British Columbia is blessed with a large forest resource base. We rely on an abundant timber supply to maintain our current level of economic and social benefits. The BC Forest Service is responsible for maintaining and enhancing forest productivity and increasing the quality and value of second-growth forests. These objectives are met through the three main activities of incremental silviculture: thinning, fertilization, and pruning. Thinning, also called juvenile spacing or pre-commercial thinning, is the removal of less desirable trees within a young stand in order to provide more light, moisture, nutrients, and room to grow for the remaining crop trees. Fertilization involves adding a mixture of nutrients that are deficient in the forest soil. This temporarily increases the growth rate of a stand, which in turn increases the subsequent volume at harvest. Pruning is the removal of the lower branches from the stem of a young tree to promote the production of high-quality and valued clearwood. This two-part program focuses on pruning. Part 1 provides the pruner with the information needed to properly prune a tree. Part 2 deals with when and where to prune, contract administration, equipment, and wood quality. As we've already seen, pruning is the removal of the branches from the lower part of the stem of a young tree. Ideally, pruning is carried out in a series of lifts, the first pruning lift height varying from 2 to 3 meters. When a branch is removed from the stem, a sheath of new growth will eventually cover the cut branch stub, producing knot-free clearwood from that point on. At present, high-valued clearwood is available only from old-growth forests. This wood has a markedly higher value than knotty wood for solid wood and veneer products because of its increased strength and improved appearance. The high proportion of clearwood in old growth is the result of natural pruning that has taken hundreds of years. Second growth, which will be harvested at a much earlier age, doesn't benefit from this natural pruning process that produces the high-value clearwood. Artificial pruning is becoming necessary if we are to maintain the same level of clearwood production from our second growth stands. Pruning reduces the occurrence of knots in subsequent wood production. Lumber that is knot-free is stronger and more appealing than wood with large or missing knots. Higher quality clearwood also sells at a higher price. Second growth wood is also characterized by a high percentage of juvenile wood. Juvenile wood is produced in the live crown. This wood is weaker, less dense, and is more prone to twisting and warping when dried than mature wood. Mature wood is produced in the part of the stem that is not near the live crown. Mature wood is stronger and more uniform in its wood properties and commands a premium on the market. Both old growth and second growth contain juvenile wood, but because second growth trees are younger and have smaller diameters when harvested, there's a greater proportion of juvenile wood to mature wood than old growth. This means the market value of second growth wood is potentially lower. Pruning can effectively resolve both the knotty wood and juvenile wood problems of second growth stands. First, by pruning a tree at a young age, you minimize the size of the knotty core. Once the knot is healed over or occluded, clearwood will be produced from then on. Secondly, once pruned, the tree stops producing juvenile wood in that area of the stem and starts producing the more desirable mature wood. Through timing successive pruning lifts, the tree will continue to produce mature clearwood in the lower portion of the stem where the most value is. Pruning is an investment in the quality of the wood produced by a tree, not its volume. It's an investment with the potential to greatly increase the value of the tree, up to threefold. Increasing the value of our second growth means that while we may be harvesting less volume in the future, we'll be able to maintain the same level of economic and social benefits we now derive from our forest resource base. Pruning must be done properly for the pruning investment to be worthwhile. It's important for the pruner to realize that poor pruning techniques can eliminate any increase in wood quality, and in some cases, even kill a tree. Wear proper clothing and protective gear to minimize discomfort and injury, including a long-sleeve shirt, gloves, a hard hat, and eye protection. Pruning is labor-intensive. It's done manually with pruning shears or a pruning saw. Do not use a chainsaw, axe, or machete to cut or knock off branches. These tools can damage a tree by leaving long, coarse stubs. Also, the impact of an axe or machete may fracture the branch inside the stem, creating a hole that can take many years to heal. Scars and holes can also provide an entry port for pests and diseases. Again, the end wood product will be degraded and the tree may die. Begin your pruning by looking for an opening in the crown as high as possible, where you can easily get your shears in close. The Ministry of Forests recommends shears be used for the first pruning lift. Shears cut cleaner and closer to the stem of the tree without scarring. These shears are designed with a flat side, which makes it easier to place them close to the stem. It's important that branches be cut straight and as close as possible to the stem of the tree. Place the flat side of the shears next to the tree for all cuts, and make your cut flush to the branch collar, which surrounds the base of the branch. Care must be taken not to damage the branch collar, as this will slow down the occlusion or healing over process. The cleaner and closer the cut is to the stem, the faster the branch stubs will heal over. Pruned branch stubs can completely heal over in 1 year. Knot-free clearwood will be produced from this point on. Angled and jagged cuts will dramatically increase the time required for the stubs to heal over and will eliminate any benefits from pruning. Small, live, and dead branches should also be removed, as they can create pinhole knots that will also reduce the benefits from pruning. Work from the top of the tree down. Use the cut branches to weigh down the lower uncut branches. This provides better access and a larger working area, and also applies stress to the uncut branches, making them easier to cut. Prune one side of the tree at a time, from the top down. Work your way around the tree, clearing each face of branches as you go. Remember to keep the flat side of the shears toward the tree at all times. The objective of the first pruning lift is to remove 2 to 3 meters of the tree height while leaving 50% of the live crown. To ensure that you don't remove too much of the tree, follow the 50% live crown rule. On more highly productive sites where trees grow faster, the contractor may instruct you to remove more than 50% of the live crown. When in doubt, use the 50% rule of thumb. Then prune up to the next whorl. The ministry recommends the use of pruning saws fitted onto axe handles or short poles for pruning lifts too high to reach with shears. Using saws on the lower branches is not recommended, as it requires more effort and doesn't provide as clean a cut as shears. While saws may cut as close as pruning shears, they can damage the tree bark. When you've finished pruning the tree to the specified height given by the BC Forest Service, do a final check around the base and stem for attached branches. Pruners are advised to keep their tools sharp and clean. Proper selection, care, and maintenance of tools will ensure maximum pruning quality and minimum worker fatigue. Pruning the lower lift using shears can be done anytime during the year. The advantage to the silviculture worker is that pruning can be done during seasons not suited for other work. Ideally, however, the best time to prune is in cold weather, when growth is minimal or the tree is dormant. This minimizes bark damage caused by the pruning equipment. To assist those involved in making decisions on where to prune, the Forest Service has developed a set of guidelines for selecting coastal and interior even-age stands for pruning. The guidelines are based on 6 key biological factors related to stand productivity, wood quality, and potential market value. Guideline 1 deals with stand selection according to species. The coast and interior have different species mixes, which are ranked in order of suitability for pruning. Pure Douglas fir, or Douglas fir mix, with Douglas fir comprising more than 60% of the stand, is the most desirable stand for pruning on the coast. Coastal western hemlock and western hemlock mix rank second, followed by western red cedar and western white pine mix. In the interior, lodgepole pine stands rank as the most desirable stands to prune. Douglas fir, larch, and white pine stands are ranked second, and interior western hemlock and cedar stands third. Spruce is not recommended because of its tendency to sprout small branches once pruning occurs. This makes it unsuitable to obtain clear wood through artificial pruning. Guideline 2 deals with site quality. The basic rule is to treat the most productive sites first, where value added will be returned first. Guideline 3 deals with stand height. In both the coast and the interior, the dominant tree should be between 5 and 7 meters in height. Guideline 4 deals with diameter size for the 5 to 7 meter height trees. On the coast, trees with a 10 centimeter DBH are the most desirable to prune. As diameter increases, pruning desirability will decrease. The smaller the knotty core, the more clear wood will be available at harvest. Because the window of opportunity for pruning stands is very narrow, follow the rule of thumb: prune young and prune high. In the interior, the most desirable stand is one with trees with 7 to 10 centimeter diameters. Again, the desirability of the stand for pruning decreases with increased diameter. Guideline 5 deals with the health of the stand. In both the coast and interior, the most desirable stands to prune should have less than 5% of the trees infected or damaged by insects, disease, and mammals. Stands having more than 15% of the trees infected or damaged should be left unpruned. Guideline 6 deals with stand density. Coastal stands should only be pruned if the spacing is below 600 stems per hectare. Stands having a higher density should be left unpruned. In the interior, pruning can be done on stands with a density of up to 900 trees per hectare. In addition to the 6 biological guidelines, 2 general operability guidelines should be met before a site is considered. The distance a crew will have to travel between the community and site is the first operability guideline. The most favorable will be good growing sites within 50 kilometers of a town. The next most favorable are medium growing sites within 50 kilometers. The least desirable are good sites located 50 to 100 kilometers from a town. Access is the last major concern in determining where to prune. If there's good access through public highways or good forest roads, then the site is highly recommended. Sites with forest roads requiring minor or major repairs are less desirable. Sites where new road construction is required or primary access is by water or air are not recommended for treatment. The stand selection and operability guidelines are general enough to allow district staff flexibility in stand selection. They are equally important, but it's up to the district personnel to evaluate different combinations since each situation is slightly different. Following these guidelines will help those involved to maximize the pruning investment. In addition to the basic contract obligation explained in the Forest Service pruning contract, the contractor should be aware of some fundamental characteristics of a pruning project. It is economically feasible to do a total of 3 pruning lifts on a tree at different ages. Part 1 dealt with pruning the first lift up to 2 to 3 meters. As the tree grows, pruners can return to the stand and prune higher to the second sawmill log. The critical point in each pruning lift is not to remove too much of the tree crown, which acts as the factory producing food for diameter and height growth. The rule of thumb is to leave 50% of the tree in live crown. On some productive sites on the coast, only 35 to 40% of the tree needs to be left with live crown. In no case, however, should there be fewer than 3 whorls of branches left on the tree. Upper lifts will require the use of pruning saws on poles. Doing upper lift pruning all day can put strain on the back and the neck, so switch crews to lower branch work daily. Stands may be spaced and then pruned on a daily basis by the same crew. During the fire season, a crew can space in the morning and prune the spaced area in the afternoon. This allows a full day of bush work rather than having to shut down at lunch. The crew can also act as a backup fire crew, as they can listen to the radio while pruning. Pruning can be a social job. There may be a tendency for conversation, so the crew supervisor may consider separating crew to maintain productivity. Pruning quality should be overseen by recording a pruner's cut path, so that they take responsibility for their own work. This can be done by using string lines within a work block. The supervisor must also evaluate a pruner's work. There are 4 major concerns: amount of ripping and scarring, angle of cut flush with tree, no attached small branches, and correct pruning height. The Forest Service should be on site the first day to ensure the standard of quality is met by the contractor. A poor pruning job can severely damage a stand. The goal is to have the job done well and help the contractor be successful. Once an area has been pruned, the site should be highlighted on all maps. Value added can easily be lost if trees from a 50-year-old pruned site are logged and sent to a mill not geared to extract clearwood. Pruning has public relation value. It offers employment, adds value to the forest, and is visually appealing. Take the time to post signs to provide information to the public when a site has been pruned. There are several varieties and combinations of tools suitable for doing quality pruning. Shears are the recommended tool for doing lower lift pruning. Some contractors prefer to purchase inexpensive shears for each contract and dispose of them when the contract is finished. Hand shears can be used to remove the small branches on the stem. Many types of saws and accessories are available for upper lift pruning. To prevent injury, make sure pruning saws are firmly attached to the extendable poles. When selecting a pole, consider its weight and stiffness. Too heavy a pole will affect the worker's productivity. A pole with too much flexibility makes it difficult to apply pressure to the saw, cutting the branch. Some saws have a bottom blade that makes an undercut, which stops tearing of the bark when the branch falls. A top blade also prevents the blade from being pulled out of the saw curve while cutting. Saws may vary in tooth design. The best is the one which cuts the cleanest with the least amount of energy. In some countries, there's a preference to using ladders to reach the upper branches. To prevent injury to the pruner and the tree, Ensure ladders are positioned and secured properly. Where there is a large amount of slash, it's going to be difficult to drag a ladder around. Platform-type ladders can also cause a lot of stem damage by the way they rest against the tree. There are other variations and types of pruning equipment. The ones shown here are the most commonly used. Wood density is an important part of wood quality, which in turn affects the value of wood produced. Les Joseph, research scientist at Foreign Tech Canada Corporation, describes wood density in a tree and how pruning affects it.
Good afternoon, ladies and gentlemen. I'd like to take this opportunity to say a few kind words about pruning and its effect on wood quality, and to answer the hypothetical question, why do we prune? Well, the most obvious reason for pruning is to produce clear wood, because clear wood commands a premium about 3.5-fold of regular lumber prices. But wood quality can be described in a number of ways. When we think about wood quality, we think about the strength of wood, the stiffness of a piece of wood, its dimensional stability. And all these attributes can be measured by measuring specific gravity in the wood, its density uniformity, its dimensional stability through longitudinal shrinkage. But first off, I'd like to make a quick demonstration and explain to you in a touchy-feely way why density is important. Specific gravity or density is an overused term. We all know it's important, but we don't quite have a feel why it's important. I have a number of sticks behind me here. This one is an exotic hardwood from South America. It's about 20-25 centimeters long. I'd like to show you what happens if I dip it in water. This wood almost sank its entire length. It so happens that it's 86% of its length has gone below water line. Therefore, the density of this piece of wood is 0.86. By the way, in South America, where they have a lot of exotic woods, they use density as a grading tool. But getting back to the Canadian, specifically the British Columbia scene, I'd like to bring your attention to the average density of a typical British Columbia softwood. This happens to be Western red cedar. Its density is about 0.35, 0.4 in this example. Just to show you what happens if I place it in a beaker of water, it had sank to this point. Therefore, the density of this particular Western red cedar stick is 0.35 or thereabouts. On the extreme left-hand side, I have a subalpine fir stick. Let's see what happens to this one. You can see, in fact, it's very light. It doesn't want to sink any more than this level. Therefore, this subalpine fir wood has a specific gravity about 0.27. So it's a very light wood. If you wanted to deliver a blow, you wouldn't want to pick up this stick. You would want to use this one because it has a heftier feel. Incidentally, density is related not only to strength but also to the heating value of wood. If you toss this piece of wood on fire, you would get a lot less heating value than from something like this. Now, at about this stage, people get sort of a cloudy vision. They get sort of bored because they heard this part of the story before. But what they haven't heard is a practical demonstration to see what happens if we subject these various pieces of wood to a strength determination. I'd like to take this stick of wood In fact, I did this first about 2 years ago. I picked it up in our carpenter shop, this very same stick, and I wondered, would this carry my weight? So I put this stick on a couple of 2x4s, and I stood in the middle with all my 190 pounds of weight undressed, and indeed it carried my weight no problem. Now let's see what happens if we take lodgepole pine. This particular piece has a density about 0.45 or so. So here is the lodgepole pine, same span, same dimensions in cross-section length. Again, it carries my weight without any problem. Actually, I'm right-footed, that's why I couldn't keep my balance too well. Let's see what happens to Western red cedar. This might break under my weight because it's fairly low density piece. Yes, indeed it did. So no doubt this one will break as well because it's low density wood. Oops. Yes, it did. In summary, I like to re-emphasize that the average density of BC softwoods is about 0.4, or in other words, a little less than half the density of water. The density of water is 1 at 4 degrees centigrade. Incidentally, according to the Guinness Book of Records, the most dense wood known to man is the ironwood. Its density is 1.4. So a piece of ironwood will sink like the proverbial rock in water. And the least dense wood known to man is the pit wood. Grows in Cuba. Its density is 0.04. In other words, 1/4 of the density of balsa wood, which is 0.16. Most of us have used balsa wood when we were kids in model building. Now, I like to get into species-specific points when we talk about density and its importance for strength and stiffness in the board. When you think about Douglas fir, we like to think that all Douglas fir trees are alike. And I can tell you at this stage that they are not alike. There are a lot of differences between trees. I have a 54-year-old Douglas fir in my hand here. This is the pit area and the bark zone. I want to show you that if I take pieces of wood from this block and I put them in water to see what happens to the wood. This is from near the pit, and I will take the outside part near the bark. So this block sank to that level, and this is the outside part sank to this level. So let's see how it fits in with the whole block. You can see that the wood near the pit is nearly 1/2 of the density of the outer wood. So if we were to draw a density trend line for Douglas fir, this is what we would get. It's sort of like a check mark. We have initially high density wood, reaches a minimum at this stage and rises very rapidly. So ladies and gentlemen, this demonstration shows that in a given Douglas fir tree, in the same tree, there are tremendous differences in density at the same level as we go from pit to bark. No doubt some of you have heard the concept of juvenile wood, mature wood. I have another demonstration here that takes a Douglas fir disc and it shows the density trend from pit to bark. This is the pit, age 10, 20, 30, 40, 50. You can see that the density for the first few rings, for the first 3, 4, 5 rings, is relatively high, reaches a minimum at about age 6 to 8, and rises very rapidly to age 30. And from there on, it settles down to a steady level. I also have marked the first 20 years of growth considered as the juvenile wood, the juvenile component of Douglas fir, and the outer mature wood. Ladies and gentlemen, at this time I'd like to revisit the density trend line with a little more attention than what I did just a few minutes ago. I have introduced the term of juvenile mature wood differences, and trees are much the same as us human beings. We go through our juvenile phase, so do trees. So if we zoom in on the cross-section again, I'd like to explain to you the specifics why density starts out initially high in the center of the tree or the pith zone, and why it falls away to a low density zone, and how it increases as a function of time. We feel initially the tree has high density wood near the pith because of the whipping action of the leader of a growing tree in the wind. And this mechanical stimulation tends to produce compression wood-like wood, and that's thus the high density. So how does the density trend line relate to pruning? And what can we do with live branch pruning to influence this trend line? If we were to prune this Douglas fir stand at age 8, this is what would happen to the density trend line. Immediately, there would be a rapid density increase in the tree, and the tree would mimic mature wood formation because of the rapid lifting of the live crown. Therefore, this strategy would help to minimize the distribution or the extent of the low quality, low density, weak juvenile wood. Even though we don't eliminate it, we would minimize it. Now the question is, why does the density trend line fall off? This trend line is based on actual measurements on trees that were pruned at age 8. And the trees were pruned to about 40% live crown. But what happened as a function of time, the tree was growing in height. Therefore, the hormonal balance of the tree was reverting back to the juvenile wood type of character. So density started to fall off again. So if we were to capture the window of opportunity in maintaining mature wood production, we would have to enter the stand a second time at about 3 years later, 3-4 years later after the initial pruning, to keep the density up at this mature wood zone level. So therefore, ladies and gentlemen, this can be explained by this trend line can be explained by the hormonal influences of the live crown. So it is very important that we manage the live crown in a responsible manner. In other words, keep it up in terms of live crown versus the stem proportion. At this point, I like to pick up the density trend line. What happens to the density trend line as a function of age in the second growth Douglas fir cross-section? We can think in human terms. I refer to the age 20 as a critical point, and it so happens in human terms, this is when kids tend to move out of home and they become independent. So once they move away from home, they are mature, although some people mature at a later age, like 40, 50. But the reason we have this density trend line is because the crown is moving up away from the lower portion of the stem. So we are producing, the tree is producing mature wood in terms of density. And as I said earlier on, mature wood is good wood because it's high density, it's strong wood. Now the question is, what happens to this second growth Douglas fir tree if we left it to grow to 100 years of age? Is this density trend line going to increase indefinitely? No, it's going to stay approximately at the same level. And at this time, I like to compare this fortuitously rapidly grown Douglas fir tree, the so-called second growth resource, compare it to the old growth resource. And here I like to show you the cross-section, a radial strip from pith to bark of a 1,300-year-old Douglas fir tree. And what I like to show you here is the proportion of the inner juvenile core, the first 20 years of growth, and contrast it with the second growth Douglas fir. And more specifically, if we did prune the second growth Douglas fir, the juvenile core would be only 8 years of growth, so significantly smaller. If we left this second growth tree to grow, let's say, to 100 years of age, it would be approximately the same size as this 1,300-year-old Douglas fir. So what we are comparing here is the proportion of juvenile wood versus mature wood. This second growth tree, if we were to harvest it at this age, at this size, it would make up the 1/2 by volume would be juvenile wood, and the other half would be mature wood. Now clearly, this old growth 1,300-year-old Douglas fir, instead of being 50% juvenile wood, it would be about 10-15% by volume. And this is where, ladies and gentlemen, the second growth resource differs from the old growth resource in terms of juvenile wood, mature wood proportion. But I also like to say that this wood is just as good, just as strong, just as dimensionally stable as this wood. The only difference is that we capture the harvest a number of times in 1,300 years. So that would be something like 26 harvests in the same time span. I'd like to bring to your attention at this stage the conceptual design or depiction of the difference between a typical second growth and old growth Douglas fir, and specifically address the concept of juvenile wood, mature wood, and basically the proportions of these two components in the living tree. Now the second growth Douglas fir at age 50 is typically around 40 meters tall, and on the average about 60 centimeters in diameter at breast height. And old growth has a much wider window, can be up to 60, 70 meter high, tall rather, and the diameter can vary anywhere from 1 meter and up. But the important thing to notice here is the proportion of juvenile wood in the second growth Douglas fir by volume is about 50%. And this is based on hard factual evidence based on measurements. So we have the juvenile wood cylinder running from the base of the tree, from the ground right up to the base of live crown. Remember in the earlier presentation I had shown that the inner juvenile cylinder runs the entire length of the tree, and it is related to the hormonal balance, if you like, the influence of the live crown on the tree. So again, at the expense of sounding repetitious, at age 20, this tree had the base of live crown down to the ground, and probably it was this tall. At age 30, the tree was up to here, the base of live crown started to move up, and at age 50 we are up here. And this is why this 20-year inner cylinder moves with us. It's a bit like a curse. It's something that we can't get away from, except if we practice intensive silviculture, early live branch pruning. Contrasting the second growth with old growth, I'm not sure if I have the shape correctly, but typically in old growth Douglas fir, the inner juvenile cylinder is only about 10-15% by volume. And we can see the inner cylinder running again like a stovepipe from the base right up. But we have a lot more mature wood envelope around the inner core. So we need further evidence for reducing juvenility in the lower part of the high-value Douglas fir. At this time, I like to compare proper pruning and a rather sloppy pruning, how it affects clearwood production. The section on my left-hand side here shows that all the branch stubs have been occluded, have been covered up, and this section still has the pruning scars showing. There's a tiny little branch about a 1/4 inch in diameter, affectionately known as a coat hanger. It still shows that it will take a number of years for this branch stub to close up. But what does early branch pruning, live branch pruning do to stem shape? If we could open up a log like I did just a minute ago, this is what we would see in terms of stem shape and cylindricity. If we look at the year of growth immediately after pruning, we can see that the ring is relatively wide up here compared to the lower portions of the stem. So if we were going to sample this tree at the base, we would see that pruning really impacted negatively. But in fact, what it has accomplished in this particular case is that it has improved stem shape and it reduced stem taper. Now I'd like to focus in on an example of proper pruning. As I mentioned, proper pruning means the branch stubs heal over. As we can see on this example, the branch stubs are covered by new growth externally here. If we were to open up this log, as in the previous example, this is what we would see. In this close-up of a properly pruned branch, we can see a very neat branch scar. Incidentally, this is about 1 centimeter in diameter. And please note that first year after pruning, we have the new growth just about covering this neat branch stub. Now, if we were to take a cross-section of an adjacent tree of similar size, and we were going to look at it closely, a very important element emerges, and that is bark thickness. Please note that this young tree at age 8 had a very thin bark. So if we were to cut a branch flush with the tree, it would result in a very short branch stub. Conversely, if we were to prune at a more advanced age, as in this example, we have two things working against us, but the most important element in this case is the thick bark. Please note that we have a branch stub here quite long. This tree was 19 years of age when it was pruned. This is how the tree was inside bark at this dotted line. Also note that the 8-year-old tree had a branch about the size of my pen, and this branch diameter is about twice the size. Also, an equally important point is that even though this tree grew 25 years from the time of pruning, we have still disturbed grain on top of the branch stub. If we were to compare a similar sized tree that wasn't pruned, this is what we would see, ladies and gentlemen. We can see branches sticking out of the tree. Please also note the swollen branch bases, and if you rotated it around clearly, this is what we would see. It is interesting to note that all branches originate or have their roots right at the pit of the central stem. Here's another one. It is also interesting to note that each branch puts an annual layer down just as the tree does. Not at the same rate, that's why the branches are usually smaller than the stem. We can also see a color difference in here related to heartwood-sapwood differentiation in the stem. Please note the darker color here. Here we have the heartwood-sapwood differentiation in the branch as well. Now I'd like to focus in on the interior bread and butter species, which is lodgepole pine, once considered a wheat species, by the way, but now it's the mainstay of our industry in the interior. What I have in my hands, this is a typical old-growth lodgepole pine. This, in fact, was one of the plus trees, 25 centimeters in diameter at 125 years of age. In my left hand, I have a second-growth lodgepole pine that's typically about 35 to 40 centimeters in diameter at age 80. So we can see the difference in size, and also I have put in here the density trend line for this particular disc. And I'd like to say a few things about the trend line that we had earlier talked about in the graph. Again, we have the pith, the center of the tree, the bark, age 10, 20, 30, 40, 50. We can see the check mark type of density trend line. Also, I have drawn in the reference line. The textbook average density for lodgepole pine is 0.41. Similarly to Douglas fir, we can consider the transition from the low density juvenile wood to the higher density mature wood at about midpoint up on this curve, and I would tentatively put it about age 25. So based on that age 25, this would be the size of the juvenile component. Now, what can we do in terms of crown management to influence this trend line and to make the tree mimic mature wood production? And again, I would advocate early live branch pruning. And it so happens we have an example here of lodgepole pine that was pruned at age 5. And I'm showing the inner core wood with the branch scars. In fact, this orange outline is the first year of growth after pruning. Conversely, we have a cross-section from a similar sized tree that wasn't pruned. And please notice the size of the branches at about age 15. So this is the unpruned control, and we have the pruned study tree. If we were to focus in on this pruned section, here we have a longitudinal section of a young lodgepole pine tree that was pruned at age 5. Here we have the center of the tree. The orange outline shows the first years of growth after pruning. So the orange outline demarcates the inner knotty core. We have two branch internodes. This is the lower one, upper one. And please note that we have nice clearwood production immediately after pruning. There is no bulging evident in the grain. We have nice vertical edge grain. The tree is nice and straight, doesn't have any bulges at the branch internode. And it's also interesting to note that even 1 year difference can make a tremendous impact on the size of the branch. This is the internode that was at the lower part of the stem. Perhaps maybe it was cut a little more messily, but I can't help but note that this branch is nice and neat, less than 1 centimeter in diameter, and the first years of growth after pruning had covered up the branch scar. So this is the upper internode. Branches were sticking out here. They were cut nice and neat, flush with the stem. Please note that even at this age, 12 years of age, lodgepole pine has very thin bark, so it was possible to snuggle up to the tree and leave a very short stub in the bark. This close-up of our control tree that wasn't pruned, this is also 12 years of age, and two things are noteworthy on this cross-section. First of all, lodgepole pine, even at this age, at 12, has naturally thin bark. Second thing is that the branches are quite big in diameter, and so we can ask ourselves, what would happen if we would prune this tree at age 12? Now, because of the thinness of the bark, we can snuggle up close to the tree, wouldn't leave big branch scars. But the problem is we have lost our window of opportunity, because if we were to prune at age 5, our knotty core would be minimized to this size, and hopefully, as a result of early pruning, this would be mature wood-like type of wood. And in the case of late pruning, we would be losing this window of opportunity, even though we would be producing clear wood from here on out. And so, in conclusion, ladies and gentlemen, this video described the basic concepts of pruning in terms that even laymen can understand. We felt that an understanding of two key points was crucial in providing the necessary information. First, clear wood production is possible in second-growth forests only through pruning. Second, pruning impacts positively on wood quality. We recommend vigorous early live branch pruning to minimize the extent of both the knotty core wood and the juvenile core wood. This is the natural wood density trend line in 50-year-old second-growth Douglas fir. The very shape of this density trend line is the result of the influence of the live crown on wood formation. The rapid increase in density from about age 10 to 30 is the result of natural crown recession. As the base of the live crown lifts up year by year, its juvenile growth hormonal influence is distanced from the lower stem. This graphic illustrates the impact of single pruning entry. Here the trees were pruned at age 8 to 40% live crown. It is noteworthy that about 2 years after pruning, the density trend line begins to fall off because the increase in crown dominance and its hormonal influence. This final graphic shows how a second lift, by first pruning at age 8 and a second time at age 12 or 13, maintains wood density enhancement. Fortunately, we have an excellent forest resource base here in British Columbia. Simply put, pruning will add value. Pruning will make this resource more valuable for the forest products industry and the citizens of British Columbia.